prove our rational roots test, we're going to want to put in p over q is equal to 0 into our general polynomial form, which is f of x is equal to an x to the n plus an minus 1 x to the n minus 1 a1 x to the first plus a0 is equal to 0. And we set it equal to 0 because we're looking for the zeros of our function. So therefore we need to set our equation equal to 0. And one more thing to note is that p over q is in lowest terms. And this may seem like, for some people, obvious because it's a fraction that we always put it in lowest terms, but it is going to become very important part. It's a very important part of this proof. And all this is saying is that the fraction is in lowest terms. For example, 10 over 2 is not in lowest terms. So this is not in lowest terms because we can divide out still. There are still common factors. So we can factor out a 2 of the top and the bottom, and that will give us 1 over 5. So now let's begin our proof by substituting p. This is a very ugly p, but that's a p. Substituting p over q into this polynomial. So f of p over q is equal to an p over q to the n, so an minus 1 p over q to the n minus 1 a1 p over q to the first plus a0 is equal to 0. And this is going to equal an p to the n over q to the n plus an minus 1 p to the n minus 1 over q to the n minus 1 a1 p over q plus a0 is equal to 0. Now the first thing we're going to do is multiply everything by q to the n in order to get rid of this fraction. If we multiply everything by q to the n, we're going to get a to the n, not a to the n, just an. I always make that mistake. An p to the n plus an minus 1 p to the n minus 1 times q. This is q to the n, so it's going to be 1 power less than q to the n. a1 p and then q to the n minus 1 plus a0 q to the n, and this is equal to 0. And now we're going to want to subtract a0 q to the n to the other side, and this may not make much sense right now, but it will. The reason for this step will become apparent in a couple of steps from now. So we subtract a0 q to the n over to the other side, so it's an p to the n plus an minus 1 p to the n minus 1 q a1 p q to the n minus 1 is equal to negative a0 q to the q to the n. And now you'll notice that on the left side of the equation we have a common factor of p. Every single one of these terms is going to have a p in it. So we can factor p out of this side of the equation. So this will give us an p to the n minus 1, an minus 1 p to the n minus 2 q plus a1p to the n, or that p will be gone actually. So q to the n minus 1. Since we're just going to take out 1p, so this p will disappear and everything else will be subtracted by 1 power of p. And this is going to equal to negative a0 q to the n. And here is where we're going to prove our theorem. Because there is an equal sign here, what this means is that this side of the equation is equal to this side of the equation. It's the same number, it just looks different. So basically what we have is a situation where two things are equal. It's the same number. So it's like 10 is equal to 10. And because p is a common factor of the left side of the equation, that means p is also a factor of the right side of the equation, because it's the same number. So like here, if 2 is a factor of 10 of the left, well, let's just talk about it in sides of the equation. If I can pull 2 out of this side, that means 2 is also, so if 2 is a factor of the left side of this equation right here, that means 2 is also a factor of this side of the equation over here, because it's the same number. So I hope everyone see that. Because this is an equation, both of the sides are the same number. If there is a factor on one side, in this case it's p, if p is a factor of the left side of my equation, then p must be a factor of the right side of the equation, because it's the same number. And now we need to use the part that I mentioned earlier. P over q is in lowest terms. So p over q is in lowest. When something is in lowest terms, that means there are no common factors that we can divide out. So like our early example, 2 over 10, there is a common factor, but this is not in lowest terms. But 1 over 5 is in lowest terms. These two numbers have no factors that we can divide out, unless they're like 1, which that's a prime factor. So we can't divide out any numbers here. So what we're going to do is we're going to take advantage of that and say, well, since p is a factor of the left side of the equation, p must also be a factor of the right side of the equation. However, we only have two terms over here. We have a0 and q. And p does not have any, and q are not factors of each other. They have no factors. So therefore p must be, so therefore a0 must be, so p must also be a factor of a0. So I hope everyone can see that. I'm trying to think of an easier way to explain it, but that's all I can. I thought of a different way of explaining it, but anyways, I can't think of it anymore. But I hope everyone see this is where the proof is really taking place. The rest of that stuff was just to get to a situation where we can prove this. P and Q have no factors because they're in lowest terms. The left side of the equation is equal to the right side of the equation. Therefore, if we can factor something on the left side of the equation, it also must be a factor on the right side of the equation. But because P and Q have no factors, therefore P must be a factor of A0. So we can write that P is a factor of A0. We don't know what that factor is. We just know that it is a factor. We don't have an explicit value for it, but we know that it must be a factor of A0. It has to be. By definition, that's what this whole thing means. So now that we've figured that out, that P is a factor of A0, it must be a factor of A0. If this function is equal to 0, then that means P must be a factor of A0. That's what this is saying mathematically. So let's move on to the next part. So we're going to write our equation back at the point where we had just multiplied everything out by q to the n. So we have a to the n, p to the n, not a to the n, a n. I did it again. It's so tempting to do. But anyways, a n p to the n plus a n minus 1 p n minus 1 q plus a1 p q, I don't know what that was, q to the n minus 1 plus a0 q to the n is equal to 0. Now what we're going to do is subtract over an p to the n to the other side. And that'll leave us with an minus 1 p to the n minus 1 q plus a1 p q to the n minus 1 plus a0 q to the n is equal to negative an p to the n. And now this time we have a common factor of q on our left side of the equation. And you can see where we're going to be going with this. We're going to do the exact same thing except for q this time. So we factor out a q of the left side of our equation. So an minus 1 p to the n minus 1 plus a1 p q to the n minus 2 plus a0 q to the n minus 1. And this is equal to negative an p to the n. And we have the exact same situation where we know that p over q is in lowest form, is in lowest terms. So this is in lowest. Q is a factor of the left-hand side of the equation. These two sides of the equation are equal. Again, we have a situation where we have the same number. 10 is equal to 10. So if we can factor something out of this 10, that means it's also a factor of this side. It has to be, because it's the same number. So since we can factor q out, that means q is also a factor of the right side. But because p over q is in lowest terms, q cannot be a factor of p. Otherwise, it's not in lowest terms. So since q cannot be a factor of p, the only other place that this factor can possibly come out of is a to the n. So we can say that q is a factor of an. And I said a to the n, I think. And I didn't mean that. I meant an. Man, this is terrible. Either way. But q is a factor of an. And this is where our proof comes from. So what we've just proved is that when we take the function of p over q at 0, then p over q is equal to a factor of a0 over a factor of an. And a0 is the constant, and an is the leading coefficient. The leading coefficient. So we go back up here. An is this term, and a0 is over here. And that's how the rational zero theorem works. So what we do, now that we know what the rational zero theorem is, we know that we don't know which factor it is, but we know that it is a factor. We know that there is a factor of a0, and we know that there is a factor of an. So what we do is just take all the possible factors and then make that pool of numbers again, and then we use our factor theorem to check and see if that solves for 0. And if it does, then it's a factor, and if it doesn't, then it's not a factor, and we continue on into the pool.